Hello there, math fans. This is partially a review for my course, but partially just an interesting discussion about circular and elliptical motion. Here you can see Harry the Husky going around my ellipse here. That's part of a visual I gave a while back when I was talking about the integral for finding the arc length of an ellipse. I did that as kind of a for fun thing when we were getting close to Pi Day. But ultimately, circular motion is all that stuff from your trigonometry days, where you learn that sine and cosine can give you points on the edge of the unit circle. And it's this important connection with circles and triangles, that if you want the x-coordinate or the y-coordinate, you can get the x-coordinate from cosine, you can get the y-coordinate from sine. If you make the radius bigger and it's not just the unit circle, there's an easy adjustment for that, which is just you multiply by the radius. So the question that I'm being asked is, how do we deal with an ellipse? And I'll answer that soon enough. But I wanted to give some background. From so various questions I've gotten this week that are related to an understanding of this is, if you choose to make this t, then that means you complete one loop from 0 to 2 pi. Okay, so the moment we choose to parameterize circular motion this way, we call this uniform circular motion. It's traveling at a constant speed around that thing. Okay, a few different things. We have this identity, so let me just say this like 2 or 3 different ways. Harry the Husky's getting in my way. Move him over here. Oops, wrong thing. You're going in the corner. So a few different things. So one thing is that cosine squared plus sine squared is always 1. So you can use that at any point, in any question, anywhere, as long as the input to the angle is the same. That also means if you throw in a number, r squared cosine squared plus r squared sine squared, you get r squared. So in general, if someone gives you a circle, of radius 3, you can parameterize it in the following way. You can say 3 cosine of t, and you can say 3 sine of t. And if you want to do one loop, you say 0 to 2 pi. Okay, so what if we want to change those things a little bit so that they're maybe not the same? In the picture here on the right, here I'll tweak one of the numbers. You can see that it's 2 and 3. So they actually have this is 2. So it's an ellipse. It looks like this. This is 3. This is 2. It turns out that's just sort of a squishing of a circle. And so there's an easy way to do that. So the quick answer is, you just change these 2 numbers, but then I'll explain why. So this is like your A, this is like your B, where your A is this number, and your B is the other. And a few different notes on that, and why that works. So here I would have 3 cosine of t, and 2 sine of t. You might say, well, you can't use the same identity, so why does that work? And you can kind of think of it in 2 steps. So one is you get the cosine by itself. This is the most systematic way to do this. And you write x over 3. You get the sine by itself. You write y over 2. And then you can use the same identity, that sine squared plus cosine squared is 1. And that means that x over 3 squared plus y over 2 squared equals 1. And this is one of the reasons that you often see an ellipse written this way, because it lends more easily to parameterization. Now, a natural question is, what if we need to go in reverse? So if you need to go in reverse, you write it in a factored form, and then from that you can see the A and the B. And I find it fairly easy to remember because I would like to plug this in here and have the number cancel. So that's how I know the x has to have a 3. I'd like to plug this in here and have the 2 cancel. Okay, so now to the question, then I'll say a few other visual things to end this up. The student's asking me a question about how would I parameterize this ellipse. Now that ellipse is not written in the standard form. The standard form would be to divide everything by 4 and write it this way. And then think of it this way. So this is one approach to the problem. And you can see I'm trying to write it in a form where it's just two things squared added together. And that's one great way to do it. So if you did it that way, then you would say, I want this to be cosine, I want this to be sine. So your final answer would be, I want x to just be cosine, and I want y over 2 to be sine. If you do this enough, you see, oh, then I can move the 2 to the other side. So I'm going to say y is equal to 2 sine. That's also going to complete a loop in 2 pi. It turns out not to be traveling at a constant speed because of the shape of it, but that's it. And that's why I can easily animate these things. I'm just tweaking these numbers. Okay, that's it. So, the only other thing you could do back here is just try to directly make it a perfect square here and here. And this also works. Here I'm thinking of, it's a circle of radius 4, so I would say 2x needs to be 2 cosine. So maybe this is less intuitive, and y needs to be 2 sine. But then I can divide the 2 out of this one, and I get the same answer that we had over here. So there's a couple different ways. Hopefully that gives you an idea. But I just thought I would end with a couple of 3D examples. So here's a 3D example. Viewed from above, this looks like a circle. That actually means it's on a cylinder. So that's what's going on. I'll expand this so you can see the equations I'm using. I'm using 2 cosine, so it's a radius 2 circle, 2 sine. I complete a loop every 2 pi. Now this one isn't a closed loop. It's sort of fun to just play around with the third component. So if I make the third component whatever I want, let's make it sine, it will then be a closed loop. And it's actually the intersection of a couple things. If I made it sine plus cosine, it's going to be a different intersection of 2 planes. If I made it 3 minus this, it's that intersection. And we can talk about how I'm parameterizing, like what it actually is. So if I wanted to say, I don't want just anything, I want a particular one, then I could just say what I want my equations to be, meaning this. So I'm going to move this over, move it here. And let's say I wanted the intersection, move a couple things around. I would like to study x squared plus y squared is 4, as well as the intersection with some random plane. How about the plane, I don't know, that goes through this at 2, 3, and 6. So that would be the plane, let's see, x over 2 plus y over 3 plus z over 6 equals 1. So it's that plane. So if I drew that plane, extended it up, intersected it with this cylinder, what would I get? Now I can draw those two things fairly quickly over here in Desmos. X to the second plus y to the second equals 4. So there's my cylinder going up. And then I can do, so this is going further. You can turn it off now. I just can't help myself. Plus z over 6 equals 1. That's that. So let's say for some reason I really want to study that intersection. I now have everything I need. I can say, well, from above, it looks like circular motion. Let's just parameterize that circle. So here we go. So I'm going to say x equals 2 cosine of t. I'm going to say y equals 2 sine of t. I know that completes one loop from 0 to 2 pi. And the only thing that's left is to describe my z. But z equals, what could I say? 6 times whatever 1 minus x over 2 is, minus y over 3. So I'm just rearranging this. And then I can put these equations here. So I do 2 cosine, and I do 2 sine. And now I can type that in. So I just go to that third component, and I say, all right, what do I want? I want it to be 6 times 1 minus just cosine of t minus 2/3 sine of t. Man, I typed something in wrong. Mission accomplished. So there we have it. That's the intersection of those two things. If I wanted to go once around, it's 0 to 2 pi. Slick. It's sort of fun to just make the other component something random. Like t to the second. Let's make a parabola on the cylinder. There's a parabola on the cylinder. Twisting parabola on the cylinder. That's pretty cool. From the side, it is actually a parabola, but since we're spinning, you can make it something more exotic. Usually sines and cosines are kind of cool, because then if you just make it a cosine of like 2t, you're going to get some wobble around it. If I make it bigger, maybe I'll make this bigger too. I don't know. It feels like the design on Charlie Brown's shirt. So we can find the length of any of those. The arc length is going to be kind of a messy integral, but you can make it pretty cool. If you just push a little harder, you can actually make it go around a sphere. So there's even more to be said here of if you play around with it a little more, and maybe I can make a separate video on that if someone's interested. This is the basic beginnings of what we call spherical coordinates. But you can now make the thing spin around a sphere in a certain way. So this would be, right now I'm trying to do x to the second, y to the second, z to the second equals 4. And, oop, I didn't get on there, did I? I lied. That needs to be a 3. Now I'm on the sphere forever. So the circular motion ideas can be extended even further. And then it's fun to play around with that. So like make the function different, change this in some way. You can have a lot of fun with this, or maybe even make that a slider. There's a lot of opportunity to be creative with very minimal effort. Like I haven't thought about that ever. So parameterizing things is pretty interesting, I think. All right, hope that it helps.